So this do now goes back to the lab on Friday. We had taken some ideas about s'mores, and we had thought about, well, you know, what if you had unlimited chocolate, but if you only had this many crackers, or what if you had limited supply of marshmallows, or whatever. And so I wanted to kind of build from that more concrete idea what we're going to be doing today. So let's go ahead and figure out. I already know from this situation here that I have plenty of marshmallows. And so we had done these mass-to-mass stoichiometry problems, which were really nice. And one of them would say mass, and the other one would say you had excess, which is good. Like if you see you have excess of a reactant, that's like a Christmas present because it saves you a whole step, a lot of work. And you don't know any better, but I promise that's the case. And so this is good. That means I don't have to worry about marshmallows, but we have 972 chocolate squares and 450 graham crackers. Some of y'all could just divide this and figure it out, but some of y'all can't, and that's okay. I can already tell you that in my head, just kind of, I like to think about work and math before I actually do it. It helps me to check what I'm thinking, because I've done AP Chem and AP Environmental. A lot of that you don't get a calculator, so boy, you better make sure you're on the right track before you start working that out by hand. Chem isn't as bad as apes, but they're both bad. So anyway, I'm looking at this, and I know that, for example, before I begin, I need 4 chocolate squares for every 2 crackers. The whole number ratio of that is 2 to 1, right? And so basically here, for every 1 graham cracker, I need 2 chocolate squares. So I really only need 900 chocolate squares for those crackers I have. So I already know that the crackers are limiting before I even start. Like if you didn't even go through that process in your mind, that's okay. But that's why I talk to you like this every day, because eventually you're going to be better problem solvers. So mathematically though, let's go on over to the balanced equation for this and kind of look at it that way. So if you think about the recipe for s'more, you know, you had 1 marshmallow, and this was, you know, excess. So we didn't have to worry about that. That's plenty, 1 marshmallow, whatever. And then, you know, you had 2 graham crackers, and then you had 4 pieces of chocolate, and that gave you, and I don't remember, you know, how they broke the letters down, but basically a s'more, which was like an M and a G and a CH. Doesn't really matter, and I need some subscripts here, but that kind of the basic thing, and this was a s'more, right? So, if I have 972 graham crackers, excuse me, 972 pieces of chocolate and 450 graham crackers, if you can't do what I just did in my head, right, what we're going to do is we're going to figure out how many s'mores we can make with the amount of chocolate we have. We're going to figure out how many s'mores we can make with the amount of graham crackers we have. And whichever one's the smallest, that's the limiting reactant. That makes sense? So that's how we're going to do it. And then when we transfer over, we'll talk about real chemicals and reactions. It won't be so bad. So anyway, let's just, I'm going to write this stuff down like this. Like option 1, graham crackers. And I'm going to label my work like this. And I'm not, I don't like to skip stuff. It doesn't help anything. So if I have 450 graham crackers, right? And I'm trying to solve for s'mores. I'm trying to figure out how many s'mores I want. If I look at my, and I know they're mole ratios, but they really are kind of like mole ratios. I have 2 graham crackers for every 1 s'more. So I have 2 graham crackers for 1 s'more, and I'm just going to write down s'more. I don't need to write all that. And so I see that I can make 225 s'mores out of my graham crackers. I mean, intuitively in your mind, if you have 450 crackers, and it takes 2 to make s'more, then you got about half that many s'mores you make. See how I'm doing that? Okay. And what I did though is I used kind of our little, you know, ratios here. So that's how many s'mores I can make off my crackers. So I'm going to go down and I'm going to do option 2. And option 2 is the chocolate. And so I had 972 chocolate pieces or chocolate squares. And if I look at my mole ratio again, I have 4 chocolates for every 1 s'more. So 4 chocolates for every 1 s'more. And, you know, when you divide that out, you get 200 and, I don't know, something. What was it? 243. Now, if you don't hear anything else I say, or haven't heard anything else I've said today, which one is making the fewest s'mores? So that's the limiting reactant. So that means when it's all said and done, it already told me I have extra marshmallows. And now I know that I'm going to have extra extra chocolate, and I'm going to run out of crackers. How do you feel? Is that the most difficult thing you've heard today? That's not that bad, is it? So, okay, what we're going to do is you can go ahead and if you need to label your hand, you can, but I bet you kind of have it in your mind now. But we're going to be using our little handy method of converting. And so the idea that we're going to be using today is very similar to the math that we were doing on Thursday, except now, I think the lecture's behind here, or not. There it is. But except now, we're going to have to basically do two calculations, and then the one that's smallest is our limiting reactant. That's all we're doing. Okay, so here we go. If you have set quantities of two different reactants, that's what just happened. I told you I had so many crackers, so many chocolates. Well, how many s'mores we can make? One's going to get used up, and the other one's going to have some left over. The limiting reactant is the one that's going to get completely used up, and the excess reactant is the one that's going to have something left over. Very simple. So, when we're doing any kind of stoichiometry where we're converting the mass or moles of one product or reactant to another, we have to make sure we have our equations balanced, because we have to have that mole ratio to get from one substance to the other, to put our hands together. So, anyway, what's the limiting reactant when 28 grams of glucose reacts with 14 grams of oxygen gas? Basically, what's happening here is this is like, I have so many crackers, I have so much chocolate, which one is going to limit me on the mass of CO2 I can make? Okay, so let's go ahead and write out the equation. This is a hydrocarbon, or it can be done in the same way that we had done those. And so if we want to write a balanced equation, glucose from biology is C6H12O6. Is that ringing a bell for you guys? And then when you eat, you also need to breathe. Yeah, so this is respiration. This reaction is respiration. Plus oxygen gives me carbon dioxide and water. Is that something familiar from last year? So any kind of hydrocarbon, when I'm dealing with this, if I'm doing combustion, I'm combining it with oxygen and getting carbon dioxide and water. And so pretty simple stuff here. What I'm going to do, remember my carbon dioxide is the same as my carbon. And then my hydrogen is half, my water is half of the hydrogen, because 6 times 2 is 12. Okay, and then I'm going to come up there and I'm going to take care of my oxygen. So let's count up our oxygens. I have 6 times 2 oxygens is 12, plus 6 more is 18 oxygens on the product side. Everybody see the 18 oxygens on the product side? Well, it's very tempting to just come over here and put a 9 here, but be careful because this one has oxygen here. So I need 18 oxygens on the reactant side. I have 6, so now I need 12. So if I put a 6 here, that'll get it balanced. And I think if you remember back to biology, like C6H12O6 plus 6O2 plus gives you 6 carbon dioxide and 6 water. Like you probably remember that from biology. And that's the reaction. So we can't do any of this converting without these mole ratios, and we can't do that without a balanced reaction or equation. So that's just good old times right there, nothing crazy yet. Okay, so that's the first step. And what we're going to be doing today is nothing different than the conversions we had already done. So what we're going to do, you're on the board with the graham crackers. We did a problem, and we found out how many s'mores we could make, and then we did a whole different one to figure out how many s'mores we could make. The one that made the fewest s'mores, that was our limited. So that's what we're about to do. Okay. So up here, it told me that I have 28 grams of glucose. And then I have 14 grams of oxygen. You know, I can't really eyeball this and tell you which one the limiting is. Not really. I mean, the molar masses are pretty complicated. This is, like, I have to do some math here. I can't really check. So, anyway, what we're going to do is we're just going to do 2 problems. We're going to solve for the mass of CO2 from glucose. And then we're going to solve for the mass of CO2 from the oxygen, that 14 grams of oxygen. And then whichever one's the smallest, that's our limiting reactant, okay? So let's go ahead with this glucose here. Now, if I'm on this ring finger, right, I have grams of glucose. I'm trying to go to grams of CO2. So I'm going to have to go from this ring finger to my palm. to get to moles of glucose. Then I'm going to have to go to moles of CO2. I'll have to go to grams of CO2. I'm going to get that done. I'm going to draw me a line. That's my option 1. Then I'm going to do it all over again. But this next time, I'm going to start with oxygen. Grams of oxygen, moles of carbon dioxide, grams of carbon dioxide. And I'm going to get that answer. Then, whichever one's smallest, my limiter. Okay? So let's go ahead and get this started. I'm going to need your help calculating up some molar masses. So, here we go. What was it? 28 grams of glucose to start with? Now what it told me? So I have 28 grams of glucose. Now I'm going to go to moles of glucose. And so I kind of made this up after the fact. But you know how we're still on this one hand? Some of you guys were making the mistake of using your mole ratio numbers when you were doing this first step. Like 1 mole is that many grams. If you're staying on one hand, it's 1 mole. It's 1 mole to get the Avogadro's number. It's 1 mole to get to the mass on the periodic table. So if you're staying on one hand, it's 1 mole. So 1 mole of glucose, it's about 180, give or take a little bit. And so you can do the math. But it's 180 grams of glucose and 1 mole of glucose. And so now I'm at the palm, I'm at moles of glucose. I'm solving for the mass of carbon dioxide, so to get from one hand to the other, I'm going to use my mole ratio. And this is where I'm going to use my coefficients in my balance equation. So I have, if I look up here, I have a 1 basically in front of this glucose. So I have 1 mole of C6H12O6. And I'm going to carbon dioxide because the question said, how much carbon dioxide can you make? Well, my mole ratio here is 6 moles of CO2 for every 1 mole of glucose. And now I'm here at my palm over here for CO2, and I'm going to mass. And so, again, I'm on one hand, so I'm going to use 1 mole. 1 mole of CO2 is about 44 grams. And this is nothing that we, we've seen this before. So I'm going to go ahead and do this work. If I can find my calculator. Not looking promising. I found it. Okay, cool. And so I get 28 times 6 times 44. And then I'm going to divide that by 180. And I get about 41 grams of CO2. So this was my option 1. Glucose. Okay, that's my first option. So if I go and I'm solving for CO2 and glucose is my limiting reactant, then I will get 41 grams of carbon dioxide. Do I know that this is my limiting reactant? No, I have no idea. So I'm going to have to now solve for the mass. If you don't have all this down, when I hit the little button, it'll kind of come back. So, so 41 grams of CO2. Everybody got that down? Alright, so now I'm going to solve for the mass of CO2 that can be made off of the oxygen. And so that oxygen, I have 14 grams of oxygen that was given to me in the problem. So 14 grams of oxygen. And I like to draw this over 1. So I'm going to go from grams of oxygen to moles of oxygen. And if I'm on one hand, I'm using 1 mole. Y'all okay back there? Okay, so 1 mole of O2. Please be careful here because it's O2. A lot of people mess up on these diatomic kind of situations. It is 32 grams for 1 mole because I have 2 oxygens.
So you do that.
I'm sorry? Yeah. So you are just whatever's in the formula you have to add up. It has 2 down there, so you got to do 2 of them. So anyway, I'm at moles of oxygen, and now I got to go to moles of CO2. When I switch hands like that, I need to use my mole ratio. And so I'm looking at my balance equation. I have 6 moles of oxygen, and that's for every 6 moles of CO2. And then I'm trying to go to grams of CO2, so I'm going to convert to grams, excuse me. So 1 mole of CO2 is, again, now the cool thing about these, because you're having to do them twice, the molar mass you already figured out the one before it. So like I told you it was 44, but if I didn't know if it was a larger compound, you can just look up, it's going to be the same molar mass because this last little conversion is going to be the same. So 44 grams carbon dioxide And so when I do this math, I end up getting 14 times 6 times 44. And then I'm going to divide it by 32 times 6. So I end up getting only 19.25 or 19 grams of CO2. Now, the other one was what, 41? This is 19. So which one's the limiting? Yeah, so that makes sense. So whichever one's making the smallest amount of your product, that's your limiting reactant. It is that simple. Any questions there? Now, tomorrow, you guys, y'all have a little quiz over these mass-to-mass conversions. It's not a limiting reactant quiz. It's just like, I'm going to give you 14 grams of oxygen. How many grams of carbon dioxide can be made? Just like this one little thing. So we got 2 questions like that tomorrow. You feel okay about this? So that's happening. Should have said that earlier, but I'm thinking about it now. So heads up. So let's kind of stop and think about this. This was my option 2. Yes, ma'am?
Why did you use glucose?
Because it told me at the beginning, like it told me I have 28 grams of glucose reacts with oxygen. So that's a good question. And so if I compare these two, 19 grams is obviously smaller than 41 grams. So oxygen is my limiting reactant. And so, you know, I can only make 19 grams of carbon dioxide. I cannot make 41. I don't have enough chocolate or crackers or whatever you like to think. All right, so on our lab on Friday, we were talking about percent yield, and I think I was telling somebody about percent error. Percent yield is, here's the deal. If you're a chemist and you're an industrial chemist and you're trying to do that for a living, I want you to understand that there's 100% yield doesn't really happen. You're going to always have inefficiencies. And they use catalysts, different temperatures, to try to get the maximum yield possible, because obviously that's something you're trying to make, right? And you want to be as efficient as possible, but you're never going to get 100% yield. And so percent yield, percent anything is part divided by whole times 100. Well, the largest that you can make, your theoretical, your maximum yield is your theoretical. So what you really get divided by your theoretical or your stoichiometry answer in this case, that's part divided by whole times 100. That's your percent yield. And so let's say if we just figured out that we should get 19 grams of carbon dioxide, right? Well, if I really did this reaction and I got 15 grams, what I actually got divided by what I should have got, or my theoretical yield, that part divided by whole times 100 gives me my percent yield. And so this is just good percent work. Part divided by whole, actual divided by theoretical times 100. And so when you go back in here in a minute, I'm going to let you guys work on y'all's lab. If you didn't get finished, y'all can go back and do this percent yield. I think I ended up talking to somebody accidentally about percent error, which is a very simple, very simple formula too. So anyway, I'm going to work out one more like this. I'm going to work all this out. You ready? If you feel like you understand this and you just want to go off on your own and see how it goes, that's fine. Catch up here when I get to the end and see if you did it right. I would say maybe like listen to one more, but some of you guys can really pick up on stuff fast. So anyway, here's the deal. I have, and I like to write down as much as I can. I have 155 grams of N2H4. All right, it's told me that. Then I have 175 grams of N2O4. And then it asks me what the mass of H2O is that I'm going to be making. So, how much water can I make? So what I'm going to do is I'm going to do 2 separate problems. I'm going to take that 155 grams, I'm going to solve for water. I'm going to get an answer. I'm going to start all the way up. I'm going to take that 175 grams, I'm going to start solve for water. Then I'm going to see which one's the smallest. Whichever one's the smallest, I'm going to do. And that's how much water I can actually make. Alright? So, here we go. 2 separate problems. So, I have 155 grams of N2H4. So, I'm on grams. I got to go to moles. So, nitrogen is 14. So, 14 plus 14 is 28. Plus 4 hydrogens is 32. And you can get you 0.00 whatever if you want. But this is 32 grams per mole, basically. Please notice how I'm writing down the compound on every single step. I'm writing down moles, I'm writing down grams. When I grade people's papers, the people that don't do well are the people that don't feel like writing 2 letters. And so you'll lose 2 letter grades if you don't feel like writing it because people don't know where they are. So anyway, I'm at moles of N2H4. I need to go to moles of water. And so if I look at my balanced equation up here, I have two moles of N2H4 for every 4 moles of water. And then I need to go from moles of water to grams of water. So I have 1 mole of water, and then 1 mole of water weighs 18 grams. And I'm rounding my molar masses just barely. Next year when y'all take AP, they'll give you the molar mass of water, and they'll give it to you as AP, no decimal places. So I'm not real stressed about 0072. I don't care. So it's not worth it today. We got to leave it for fish to fry. So anyway, I'm going to go ahead. This is my option 1, right? N2H4. And I'm going to go ahead and solve here. And so when I do that, I'm going to figure out how much water I can make from this 155 grams. And so I find out that I can make 174 grams of water. Now, I don't know if that's really how much water I can make. I don't really know. The other one could be small. So we have to do the other one too. So this is my first of 2 options. That's my first option. I've done nothing here that you didn't already know how to do. So let me show you that again. So there's their math if it looks nicer and prettier than mine. Now, like I said, this is just one of the 2 choices. I have to work the other one out same way. So I'm going to start with that, I think it was 175. Let me see. Yeah, 175 grams of the N2O4. You guys got this part down? Got it? Okay, so now I'm going to start with 175 grams of the N2O4. So 175 grams of N2O4, and I'm going to do the work to find out how many grams. Oh no. Okay, how many grams of water I can make. Crazy. So 1 mole. Okay, so I'm right here on this finger, and I gotta go to moles. So 1 mole of N2O4. That's 28 plus 64 is what? 90? Is that 92? I don't know. Sometimes I do math and I'm like, I don't know. So 28 plus 6. Yeah. Okay. So 92. So 92 grams of N2O4, and that's the mass of 1 mole. So there's my molar mass. Now, I'm at moles of N2O4, and I got to go to moles of water. So I'm going to use my mole ratio. Tomorrow on your quiz, I want you to see my hands doing that, and I want you to hear me say that. I want it to be internalized, and you be scarred for life. So 1 mole of N2O4, and I'm again, you know, this is what I'm trying to figure out how much water I can make. I have 4 moles of water if I look at my mole ratio. And then this last fraction is going to be the same. So we already did the molar mass. So 1 mole of water is 18 grams of water. And now I'm going to solve and see how much water I can make from the N2O4. So I got 137 grams of N2O4. So is this our limiting reactant, or was option 1 our limiting reactant? Yes, ma'am.
Is it supposed to be N2O4 H2O?
Oh, yeah, thank you. Thank you so much. And, you know, I'm glad that Leah said something, because on my own papers when I'm working stuff out, like, I do this and I circle this, and then I'm very careful. So, yeah, so thank you. It is water. So That's how much water can be produced from the N2O4. So was this one less or was option 1 less? This one. So N2O4 is my limiting reactant. And so this is actually the mass of water that can be produced, 137 grams. Not what we got on the last one. We can't make that much. We don't have enough. So how do you guys feel? Okay? Alright. On the next slide, it's going to ask us, after I kind of show you the work here one more time. So I can see that, obviously 137 grams is less than 174, so N2O4 was limiting, and 137 grams could be produced. And so now we're going to extend that again to percent yield. And so if I only make 129 grams of water, what you actually got, or your experimental yield, divided by your theoretical yield. This is, in theory, what I got according to stoichiometry. So part divided by whole times 100. And I mean, this is probably in the 90s. 94.2. Okay. So 94.2% yield. So that's how, so that's pretty easy. Sometimes if you really make a pretty bad error in a lab, or you don't quite separate something out, you can get above 100% yield, but it's probably because you didn't really get over 100%. That's not possible. But it's because you made some kind of significant error. So there's that. And so what I want you guys to do now, your lab on Friday, I told y'all to stop at number 19. And so I want you guys to pick up at number 19, work through the rest of that. Also work through that copper lab. And then we can work through some of these practice problems, okay? And probably want us to get through maybe like the first 3 or 4 practice problems after this packet, or after this lecture. So let's finish up our labs. Kind of can extend that percent yield to the copper lab, and then 19 through the end on the marshmallow lab. Thanks.